Hey everybody, welcome back. So we are going to just continue right along here. We're going to actually do the concave mirror array diagrams. So for those of you who haven't seen the previous lesson, go on, have a look at the anatomy of a curved mirror array diagram because it will certainly help you out with this lesson. So without any further ado, let us begin. I'm going to begin by drawing my principal axis. So here I've drawn a straight line. Of course, as I mentioned already, you guys will use a ruler for this. When you guys are doing this, what I would like you to do is put the protractor down where the 90-degree mark is on this principal axis so you can actually draw a nice curve around here. So I'll give you guys a second to do that. You guys can pause the video there. I want you guys to measure the distance between the edge of your protractor and the point where your 90-degree line crosses the 0-degree line on your protractor. Make a point right there. So if I was doing this, basically it would look something like this. I would have my protractor marks here, and then I'd have a 90-degree line and my initial line. I want you to mark that point on the protractor and put a mark there. Now the protractor's half circle, so that means that that point that you've just marked is the center of curvature. Now measure that point's distance from the vertex. Usually they're around 5 centimeters or so, or whatever the measurement is. Take that measurement, divide it by 2, and that way you'll know where to place your focal point. Now it's really important that you do this, and if you don't want to use a protractor, you can always use a compass. But in any case, I always use a protractor. It just makes my life really easy. So I've drawn now the backbone of my curved mirror ray diagram. Now we have to be specific because there are 5 different ray diagrams that you're going to be doing. So this first ray diagram is labeled beyond C. And what I mean by that is our object, which of course we're going to use an arrow, is going to be after the center of curvature. So I'm going to draw that right here. Here is my arrow. Color it in. Nice little arrow there. Now, I want the arrow's bottom to be sitting on the principal axis and the tip of the arrow at any height. It doesn't really matter, but don't make it too big. When you are doing these ray diagrams, you're going to do the exact same light rays every single time, no matter what. So your first light ray is going to leave the tip of the arrow, and it's going to travel parallel to the principal axis until it hits the mirror. So we'll put a little arrow there because it's moved in that direction. When it strikes the mirror, as we saw from the previous lesson, because it's parallel with the principal axis, it will reflect so that it crosses the focal point. And of course, this will go off to infinity. Now, of course, you guys will make it look a lot nicer using a ruler, but you get the point there. So that light ray will go off into infinity. The second light ray you will always draw will also be from the tip of the arrow, and that light ray will go through the focal point, and when it strikes the reflective surface, it will reflect backwards parallel to the principal axis. Now that should make sense to you. If the first light ray is traveling parallel to the principal axis, strikes the reflective surface and bounces through the focal point, then the second light ray, which travels through the focal point and hits the reflective surface, should bounce back parallel. Now, in order to be able to see something, you have to have light rays converging to a point. So if you recall when we did the plane mirrors the other day, you ended up with light rays converging behind the mirror. Of course, these were imaginary light rays, which we call virtual light rays. They converged behind the mirror and an image was formed. In this particular case, you have light rays actually converging together on the reflective side of the actual mirror itself. So I'm going to draw my object here. Now, you'll recall the other day that we did need 4 rays to determine the image that is going to be produced. You have 4 rays in this one, you just don't realize it. The second set of rays would be drawn, if we were to label my arrow point A and point B again. they would have been drawn, I'll zoom in for effect there, they would have been drawn from point B, which is at the bottom here, traveling right along the principal axis, striking the mirror, and then traveling right back. That's the first one, and it bounces back at the or through the focal point. And the second one would have gone in that same direction, through the focal point, hit the mirror, and bounced right back. So you actually have 4 lines, even though we've only drawn 2. Now, why did I draw this arrow upside down? Well, I drew the arrow upside down because the 2 light rays that are converging here, where this arrow is, represent the tip of the arrow right there, because they're the light rays that left there, and they are going to converge back. And so we have produced our first diagram here. Now we have to, of course, describe our image using lost or salt, if you want to use salt. So in terms of our diagram, location is represented by the letter L here. So what is the location of the image relative to the object? Is it closer, farther, or the same distance from the mirror? Well, in this particular case, my image is closer to the mirror, or closer to the vertex, than my object is. Remember, this arrow is the object, and this arrow here is the image. That's what's produced. What about its orientation? Well, if you take a look at the object, the arrowhead is pointing upwards. If you take a look at the image, the arrowhead is pointing downwards. And so we have an inverted image for our orientation. In terms of size, you can take your ruler and measure it if you'd like. It is a smaller, the image itself is smaller than the object. And then in terms of whether the diagram produces a real or a virtual image, these are actual light rays converging together to produce this image. And so we have a real image here. So that's what happens when our object is placed beyond C. The next one I'm going to draw, and we're going to do the exact same process. So we have our principal axis, we have our curve there. Of course, the pen is being a little finicky. We have our focal point, we have our center of curvature. Get it there. We have our center of curvature, the point where the mirror crosses the principal axis, that's called our vertex. The next one that we're going to draw is going to be at C. So we're going to place our arrow at the center of curvature, sitting right on that center of curvature point. So at this point, I'll give you guys a second to catch up because I don't want you guys to fall behind. And what I want you to do is attempt this by yourself. Hit the pause button on the video in case you want to catch up and try it yourself. Follow the rules that I just laid out for you. And when you're ready, unpause it and I'll go through it. Okay, so here we are. Let's go through. Here's our rules. My initial rule was, of course, take a line that leaves an array that leaves the tip of the arrow and travels parallel to the principal axis. Of course, it will strike the principal axis, and where it strikes that principal axis, we are going to have a reflection happen, and that reflection is going to travel through the focal point. And you'll have your second ray, which will travel from the tip of the arrow through the focal point, extend its way down, and then, of course, travel across into infinity. And where those 2 points meet, you can produce your image. Now, of course, I freehanded this. It'll be a lot nicer when you do it on your particular diagram. But if you've done this correctly and all of your measurements were good and whatnot, you will produce that image. And now the image that you are going to produce, we have to describe using lost. So let's go ahead and describe it using lost, L-O-S-T. So its location, as you guys can see, the image is at the center of curvature, so it's the same distance as the object. The image is inverted. As you guys can see, The arrow from the object is facing up, and the arrow from the image is facing down. The size is the same, and you can measure that with your ruler. And the type of image is a real image, as those are actual light rays that are converging. So we've done beyond C and we've done at C. The next one that we are going to draw is going to be between C and F. So let's go ahead and draw that out. So we've got our focal point, about twice this distance. We have our center of curvature, focal point, vertex. And so I'm going to place my arrow somewhere in here, between C and F. And we're going to follow the exact same rule. So if you're ready, you can pause the video, try it out for yourself. Otherwise, I'm going to start in about 2 seconds. All right, hopefully that all worked out for you, and hopefully you get this as your answer. So the first light ray always leaves the tip of the arrow, travels across parallel to the principal axis, strikes the reflective surface, and reflects through the focal point. The second one will leave the tip of the arrow, it'll go through the focal point, strike the reflective surface, and when it strikes the reflective surface, it will travel parallel to the principal axis. Once my pen starts working again, parallel to the principal axis, and it will continue on into infinity in that direction. And so my arrow is now drawn over here. All right, so let's describe our image using lost. So its location clearly is farther. Its orientation still inverted. Its size is larger now. The image is larger than the object. And the type is still a real image. Those are still actual light rays that are converging. And so this is between C and F. If I continue this on, I have a little image down here. And I don't know why it's there, but that's okay. Let's just move it off to the side for now. The next one here is going to be at F. So this is the next one. So here's my F, here's my C, and my V. So V, F, C. And so this next one here is at F. And so when we are drawing this, we're going to make sure that our arrow is sitting right on the focal point. And at this point, I'd like you guys to pause, try it out, and see what happens. Okay, welcome back. In terms of what you probably tried to do is you probably tried to follow the rules and you realized that they quickly broke down. So let's try this out here. So my first light ray will work just as we planned, right? It will leave the tip of the arrow, it will run parallel to the principal axis. When it strikes the reflective surface, it will reflect backwards through the focal point. The second one is where the problems start coming. So if I tried to take my arrow and I tried to go to my focal point, I'd be going right through the stem of the arrow and it would travel straight down. Of course, if it travels straight down, it is not going to strike the mirror. When you have an object sitting at the focal point, the image actually disappears. There is no image formed. Okay, so there is no image at the focal point. And that's because the light rays, which you of course are trying to see, you're trying to see the reflected rays, there is no reflected ray that can possibly produce an image there, and so you don't produce an image. Okay, last one here. And this one I want you to just be very careful. I'd like you to extend the principal axis further to the right. I know in the other diagrams up above, I've been drawing them with the principal axis, the mirror crossing closer to the right-hand side. Put the mirror closer to the center. So here I'm going to draw out my diagram here. Now, this one, you can already imagine where it's going to be. This one's going to be between F and V. So if we're going to draw it out, here's my V. Here, let's say F is right here. And let's say C is somewhere twice that distance. And so we are going to place my my object between F and V. Let's say it's somewhere at this point like that. Okay, so I'm going to pause, give you guys a couple of seconds, and see if you guys can figure this out. Okay, welcome back. As the light ray leaves the tip of the object, it will travel towards the mirror. It will strike the reflective surface, and it will make its way towards the focal point and cross the focal point as we already tried. The second one is a little bit tricky with this particular diagram. Now, if the light ray were to leave the tip of the arrow and go to the focal point, you could see very quickly that it's traveling away from the mirror, and so we're not going to get a reflected ray there. However, you have to remember, back to our first lesson, that when we have an object, there are an infinite number of light rays that leave that particular point on an object, and they go in every possible direction. So that means that there is a light ray that has a light, or sorry, there is a light ray that leaves the object in the same direction as if that light ray would have come from the focal point. So something that looks like this. So you'll notice that that light ray left the tip of the arrow as if it was coming from the focal point. And when that light ray strikes the mirror, it will reflect parallel to the principal axis, just like all of our other ones. And we have a problem here. The problem is that our two reflected rays are diverging. They're moving away from each other. So the first ray that I drew, this one here, will never cross paths with the ray up above, ever. And so as a result of them not crossing paths, we can't possibly produce an image. And if we can't produce an image, then there is not going to be an image. But our brain is this really, really, really powerful computer, and it's able to see these light rays and extrapolate from where did they come from. And so if I take my reflected rays, as I did in the plane mirror, and connect them, or extend them, I should say, backwards behind the mirror, you'll see that at some point they would have crossed one another. Where they cross, that represents the same point on the arrow where this is actually occurring. And so I do produce an image here. This image is able to be described here. So in terms of what we're actually going to do here, we're going to describe this image as best we can. So clearly, the first thing that stands out here is its size, and its size is much, much, much larger. And the other thing that you'll notice is that the object, in comparison to all the other diagrams we've done, what's its orientation like? Well, its orientation is clearly upright. I'll give you guys a second to figure out its location, and you can do that using your ruler. So just you want to measure from the vertex to the object and the vertex to the image. I'll give you guys a second to do that. So you'll clearly find that it is farther away. And then, of course, the type here, the type is going to be a little bit different. Well, the type in this particular image is going to be a virtual image, because these light rays, this one here and that one there, are not real light rays. They don't actually exist. Light rays don't go through mirrors. They bounce off of mirrors. Now, the question is, how do I know if I've been doing these all correctly? Well, that's a pretty tricky question. If you've drawn everything correctly, there is a way to check that everything is correct. Now, of course, bear with me, I've drawn everything freehand. I'm just going to change the color of my font here. I'm going to change it to, like, let's say a blue. Actually, maybe I'll do a green. So there is a way to check whether you've done this correctly or not. And the way to check is to take your ruler or your protractor, take the straight edge, connect the center of curvature to the tip of the object. And what should happen is, if you've done this correctly, there should be a line you can draw that goes from the center of curvature to the tip of the object to the tip of the image in each one of them. So there's my first one. Remember, I freehanded that. There's obviously no image here, so there's nothing to check here. This one, again, you can see that they do connect, okay, in that direction. If I go here, these ones obviously connect because it's top to bottom, right? So there's my next line. And then over here, and this one was freehanded, so it's not great, but anyways, you get the idea. It would go something like that. Now, why does that happen? Why can we check with that? The reason you can check with that is because if a light ray leaves the center of curvature and goes to any point on the mirror, it doesn't matter where on the mirror it goes, it's always hitting at a 90-degree angle. Think about that. Here's my center of curvature. Here's a curve that goes around. If I leave here, that's the radius of this circle. It strikes, and I'll zoom in here so you can see, it strikes at a 90-degree angle, which means that if this is a light ray, hits the mirror, how's it going to bounce back? Well, it's going to bounce back right along the same line. Same thing here. Leaves here, strikes the surface. It's always at a 90-degree angle, reflects backwards. So when we look at the check lines here, if a line left from the tip of the arrow in the direction of this green line, it would strike that green line and bounce back towards that center of curvature. Same thing here. And this one's a little harder to see because the line isn't that long, but if I go back here, if a light ray leaves the object through the center of curvature and strikes the mirror, and of course the pen's not going to work, there you go, strikes the mirror, it's going to be striking at a 90-degree angle, and so it reflects backwards. So those are your 5 diagrams, 5 possibilities for your concave mirror ray diagrams. Now, where do you see this? Where do we have these mirrors? Well, they're all over the place. All of these, you can actually go and test this out right now. Most people will have this in their homes. If you have a makeup mirror, one that makes you look jumbo-sized if you're nice and close, that only happens if if your face is between the vertex and the focal point. If you actually take that mirror, look at yourself very large, and then slowly pull the mirror back, you will eventually disappear. You'll invert then. You'll still be large, but inverted. Keep moving backwards. Eventually, you'll be inverted, but the same size as you are in real life. And then, of course, if you keep going backwards, you'll continue to get smaller. You guys can try that. I implore you to try that, because that's exactly what these images are here. So that's the lesson on how to do concave mirror ray diagrams. I hope that was helpful for you guys. If you have any questions, send me an email. Thanks.